morning and welcome to AdvaMed's Congressional Briefing on Precision Medicine, Genomic Sequencing and Diagnosis. It's an exciting and timely topic for the industry, and we look forward to your participation. My name is Cecilia Lopez, and I will be your host for today's webinar. We also have a team of staff behind the scenes running the technical portion of this program, monitoring questions and troubleshooting. Just a few reminders before we get started. If you experience any technical difficulties during the webinar, first attempt to exit the broadcast and rejoin. There is a link to a general troubleshooting guide in the chat box currently as well. If any of the panelists experience audio or technical difficulties, please let us know using the chat function. Please note that this session will be recorded and will be provided to you along with the slides in a post-event email within 24 hours. Each participant is currently in listen-only mode, meaning that your line is muted. There will be an opportunity for questions at the end of the presentations. If you have a question, please use the raise your hand feature located at the bottom of your screen. Staff will call your name and announce when your line is unmuted, and you may then ask your question. In taking live questions, please remember that today's broadcast is being recorded, and by asking a live question, you consent to being recorded. You may also enter questions in the Q&A tab at the bottom of your screen. This concludes the housekeeping portion of the webinar. It is my pleasure to now introduce our moderator, Susan Van Meter. Susan is the Executive Director of AdvaMedDx. Welcome, Susan, and thank you for getting us started today.
Great, thanks so much, Cecilia, and welcome everyone for joining this session. As Cecilia said, I'm Susan Van Meter. I'm the Executive Director of AdvaMedDx. We are a trade association that represents manufacturers of diagnostic tests and technologies in the US and abroad. Diagnostics are foundational to inform clinical decision-making across the continuum of care. Diagnostics enable early detection of disease, facilitate evidence-based medicine, guide clinical pathways, and monitor disease to improve patient and public health and healthcare. There's a great breadth and depth and array of diagnostics available to patients and clinicians today. Globally, we recognize this day as Rare Disease Day. And today's panel discussion is focused on genomic testing, specifically on the diagnostic tool of whole genomic sequencing and the tremendous utility and benefit these tests have in helping to identify undiagnosed rare genetic diseases. Rare genetic diseases affect about 350 million individuals worldwide. Estimates are as many as 10 million of those individuals reside in the US, with about half of those being children. For these children and their families and caregivers, a typical pathway for care can take 5 to 7 years on average to arrive at a diagnosis and treatment plan. These years can feel rather like a diagnostic odyssey, with a confusing road of testing and sometimes incorrect treatments, even misdiagnosis for children with these rare diseases. During this time, conditions can actually worsen or become more difficult to manage. So getting to the heart of the condition and knowing the genetic cause of a disease more rapidly can mean actionable diagnosis, leading to changes in treatment and management of the condition. Whole genomic sequencing is the most comprehensive genetic screening available, and utilizing this powerful tool as a first-line diagnostic can mean a world of difference to these families and caregivers of children with rare diseases, including a financial difference, psychological difference, to name a couple. While the cost of sequencing has decreased dramatically in recent years, states have been slow to provide coverage for these tests. Last Congress, Congressman Scott Peters, who's with us today, introduced the Ending Diagnostic Odyssey Act, which would give states the option to conduct a 3-year pilot program to cover 75% of the cost of a child's whole genome sequencing through Medicaid for the first 3 years, incentivizing states to cover the remaining 25%. This investment in diagnosing illness more directly and quickly would not only save lives, but it would reduce medical costs. The legislation has the potential to build upon the promise of the 21st Century Cures Act, furthering the emerging field of precision medicine. Now I've got the pleasure to introduce to you our panel of distinguished speakers who will go into more detail about this powerful diagnostic tool for rare disease. First, as I mentioned, Congressman Scott Peters, who's with us. He serves California's 52nd Congressional District. First elected in 2012, he currently serves on the House Small Business Committee and the House Energy and Commerce Committee, where, among other priorities, he advocates for investment in scientific research and common sense healthcare reform. As stated, he's the lead sponsor for the Ending Diagnostic Odyssey Act introduced in Congress last session. Dr. Eric Green is also with us. Dr. Green is the director of the National Human Genome Research Institute at the National Institutes of Health. He's the third director of the Institute and was appointed in that role in 2009 by NIH Director Dr. Francis Collins. Dr. Green's relationship with the Institute has began long ago. He served in many roles in the Institute, including as founding director of the National Institutes of Health Intramural Sequencing Center from 1997 to 2009. Prior to that, he played an integral role in the Human Genome Project. Throughout his career, Dr. Green has authored or co-authored over 375 scientific publications. I'm pleased also we have Ms. Sharon Terry joining us today. Ms. Terry is president and CEO of the Genetic Alliance. It's an advocacy organization of 10,000 organizations and individuals. Importantly, the Genetic Alliance works to further biomedical research and to provide programs and tools for ordinary individuals to take charge of their health and healthcare. Further, she has founded PXE International, a research advocacy organization for the genetic condition pseudoxanthomia elasticum, or PXE, in response to the diagnosis of two of her children in 1994 with PXE. With others, she has co-discovered the ABCC6 gene. Mutations in that gene cause PXE. Ms. Terry patented it to ensure ethical stewardship in 2000 and assigned the rights to the foundation. She has subsequently developed a related diagnostic test, supports clinical trials, and has authored over 150 peer-reviewed papers, 30 of which are relevant to PXE clinical studies. Finally, we're very pleased that Dr. David Dimmock has joined us as well. He is Senior Medical Director at Rady Children's Institute for Genomic Medicine in San Diego, an internationally renowned expert in the field of clinical genomic medicine. Dr. Dimmock is passionate about improving the standard of care for children and adults with inborn errors of metabolism. Through 20 years of clinical experience, his medical practice has been focused on the identification of rare disorders through newborn screening and advanced genomic technique. He is especially recognized for bringing innovative diagnostic testing strategies to the clinic. I'd now like to introduce our first speaker again, Congressman Scott Peters, who will give some opening remarks about his efforts to help end the diagnostic odyssey for seriously ill children. Congressman?
Thanks, Susan. I want to begin by thanking AdvaMed for putting this panel together. We struggle a lot in Washington, D.C. with the role of innovation with how to make sure that we take the innovation that's happening in the economy today and apply it to healthcare in a way that brings not just better results, but more cost-effective results. I think we can save a lot of money with this technology. And the best way to think about that may be in thinking about rare diseases. So rare genetic diseases, as you mentioned, affect approximately 6 to 10 million Americans. Half of them are children. As you mentioned, it can take up to 7 years to properly diagnose children suffering from a rare disease. In this time, countless families experience too many expensive, unnecessary tests, too many days spent in a hospital, and far too much guesswork, not to mention the pain that parents must have when they expect to go to the doctor and be told what's wrong, and the doctor just can't provide that diagnosis using those old technologies. So the gauntlet has come to be referred to as the diagnostic odyssey among providers. And the good news is that technology today can provide a solution. Genetic testing yields rapid results and can ensure children receive appropriate treatment as fast as possible, potentially saving their lives when traditional diagnostics fail to pinpoint a condition. So today's panel will talk more about how the diagnostic process is changing as genetic testing becomes the standard of care in the field, as standard as any routine lab test. And many of these achievements in genomics and genetic sequencing stem from cutting research that I've been able to observe in my backyard in San Diego, California. In San Diego, we've shown the world what happens when the research community, institutions like the Salk, Scripps Research, Rady Children's Institute for Genomics Medicine, collaborate with companies like Illumina and Human Longevity and the J. Craig Venter Institute, as well as with hundreds of local incubators and accelerators that bring in hundreds of millions of dollars in VC capital and talent to our region. The results are revolutionary. And I know you're going to hear about Project Baby Bear, but I mean, we'll all repeat each other, but I was just so impressed when I saw that what Rady's Children's has done with Project Baby Bear. They said they provided whole genome sequencing for hundreds of their pediatric patients. To date, 43% of those children whose genomes were sequenced received a diagnosis that explained their illness. 31% received a diagnosis that caused a change in treatment. And sometimes the answer was as simple as adding a vitamin to the child's daily routine. Over the course of the project, they spent $2 million on sequencing, and in doing so, they've saved children 513 days in the hospital, 11 fewer significant surgeries, and 68 additional genetic or diagnostic tests. When taking into account all these procedures, the project saved nearly $2.5 million. And you know, we want to talk about this $2.5 million. That's in addition to whatever lost earnings or chronic treatment would have happened down the line that was prevented because we got the diagnosis right at the beginning. So genetic and genomic sequencing is revolutionizing the way that we screen, prevent, and treat rare diseases. It's cost effective. It helps provide answers to families faster and can drastically improve patients' lives. And I hope that you'll get to see some of the pictures of these kids who've gone from being significantly impeded to living just a normal kid's life because we could diagnose their problems early and correctly. Unfortunately, there's some barriers to access to genetic and genomic testing, including the lack of insurance company coverage, the lack of adequate NIH funding, and a regulatory environment that can stifle innovation. I often say that Washington, D.C. is not, it's sort of where innovation goes to get stopped. It's not the culture of thinking with great hope about tomorrow all the time. In California, I know in San Diego, we have that sense that tomorrow's a challenge that we can take on, but this frightens a lot of people. That's why the education that you can all provide is so important, because Congress can fix this. Last Congress, there were multiple legislative efforts to increase access to genetic testing for families that could otherwise not afford it, including the bill that you mentioned, my bill, the Ending the Diagnostic Odyssey Act. This term, we're anxious to bring together everyone who wants to help expand access to these critical services to the families and the patients that need them the most. It's hard enough for parents and families to face an unknown medical future for a young child, and they should have access to every available diagnostic tool to give them the answers they so desperately need. And from the country's perspective, we should think about how to employ technology that's available today to get better diagnoses that can save us money, in addition to providing better care down the line. So I want to thank you for having me here today. I'm going to turn it over back to you, Susan, and to the experts. But I want you to know that you have a willing partner here in Washington, D.C. We really want to get the word out about this, and we want to make sure that we get the market adjusted so that it takes this on, and that we do take advantage of what we can do to improve the standard of care for every patient and every kid. So thanks for having me, and best of luck today.
Thank you, Congressman. Thank you for your leadership and your passion on this issue, and we look forward to continuing to work with you to help expand access for all children to genetic testing. Thank you, sir.
Thank you.
At this time, I want to introduce our next speaker. Please welcome Dr. Eric Green, the director of the National Human Genome Research Institute. Dr. Green, go ahead, please.
Well, thank you very much. It's great to be here. Let me immediately start by thanking Congressman Peters for joining us today. He is genuine. In fact, I don't know if he remembers or not, but back in 2013, he came to the NIH campus, and I, along with my clinical director at the National Human Genome Research Institute, Dr. Bill Gall, gave him a tour of the clinical center, and we sat in a conference room and talked about these diagnostic odysseys that patients face, some of which come to the clinical center now as part of a program called the Undiagnosed Diseases Program. And Representative Peters had excellent questions, was deeply moved by what he heard and what he saw, and it was really a pleasurable visit with him that day. So I really appreciate his interest in this area. I've been involved in genomics really since the beginning of the field. I got involved in the Human Genome Project at a very junior stage in my career, and have seen it all the way through, and I'm now fortunate to lead the institute at NIH that was created to lead the US's effort in the Human Genome Project. And all of this, of course, is a journey to advance human health, including for patients with rare diseases. But let me give some context to all of this, and I think it'll fit nicely with what you're going to hear from other speakers. Just to make sure everybody's on the same page, we're talking about the genome. We're talking about a concept of studying of all of the DNA of an organism, in the case of the human genome, in the case of what we're talking about with medical applications. And DNA consists of these 4 building blocks, and the 4 building blocks we abbreviate for simplicity by 4 different letters. But when you hear about sequencing a human genome, it's really about ordering these letters across all of human DNA. And the human genome's big, but it's finite. It's about 3 billion letters, or 3 billion of these bases. And the idea from the late 1980s was, wow, wouldn't it be wonderful if we were able to have the actual sequence, the actual order of all these letters in a human genome? And maybe someday, if we had that information, we'd be able to extract differences in each of our genomes and figure out if any of those differences play a role in our health and disease. That was really the conceptual basis for this project called the Human Genome Project that took place from 1990 to 2003. It was this big international effort that involved scientists around the world coming together and actually organizing themselves and then reading out for the first time the 3 billion letters that make up the human genome. I won't take you back to all the details other than to say the project was wildly successful. It was gratifying 18 years ago when the project ended because all the goals had been achieved. And we had not only generated a reference sequence of the human genome, we made that available to the worldwide community and everybody through the internet, completely free access so that everybody could build on that. Many things have come out of it, but relevant to today's briefing and relevant to the institute I lead at the National Institutes of Health has been the obvious desire to then pivot from having the most basic information about our DNA blueprint to actually start to use information about individual patients' blueprints as part of medicine. You'll frequently hear this referred to as genomic medicine when it's really focusing on the genome. And the idea of genomic medicine is, can we get to a point where we can read out or analyze a patient's genome and use the resulting genomic information, in other words, the few number of spelling differences they may have in their DNA, in some way to either diagnose a disease if they have it, or just learn something about the best way to manage that patient, to keep them healthy, or to deal with them if they do encounter diseases. Now, that was not going to happen overnight. And in fact, the journey to get to genomic medicine is still certainly in progress. But we started 18 years ago when the Genome Project ended. That was the starting line for this journey to genomic medicine. And the aspirational goal is change the practice of medicine so we manage and treat patients based on their unique genomic blueprint. We had many steps to go along the way. We didn't even know what all the steps were going to be 18 years ago when we started this next phase of our journey, but we knew what some of those steps were, and we've made a lot of progress in 18 years. I would say the number one thing that has changed the topic that we are talking about today, especially for rare diseases, has been our ability to actually read out the human genome sequence. Because when we did it for that very first time and finished it 18 years ago as part of the Human Genome Project, we were wildly successful at achieving that goal. But it wasn't very cheap. It cost about $1 billion. Now, it was money well spent, but that was a little too expensive for a clinical test. And one of the goals we explicitly stated 18 years ago when the Genome Project ended is we needed to reduce the cost of DNA sequencing, and we needed to do it not just a little, we needed to do it by 6 orders of magnitude and be able to generate a human genome sequence for something like $1,000. In fact, that became a battle cry. The $1,000 genome became a battle cry for research funders like my institute that got all sorts of scientists developing new technologies. It also became a battle cry for the private sector, and multiple companies embraced this and commercialized new technologies when they came available, including technologies such as Illumina, which is in the congressman's district, where major companies and others have developed technologies that have successfully reduced the cost of the sequencing of human genome to less than $1,000. And what that has put us in is that now actually reading out a human genome sequence is trivial. It's not expensive. You can do it, as you'll hear from another speaker, in less than a day if you had to, but you can certainly do it in a few days pretty easily. It's happening all the time. And the great news is that the technology is no longer the barrier. It's not to say that everything else is simple. So that was just the first step, was actually getting the technology to be able to read out human genome sequences inexpensively and quickly. We also then have to understand how all these letters work, how they choreograph all the complexities of human biology. We needed to know where all the genes were. We needed to understand how all the genes worked. We are working hard at this. We've made great progress in 18 years. We will probably spend another couple decades teasing out all the nuances and all the complexities in those 3 billion letters. But you can now go to browsers like you see here on the internet, and you can surf and dig deep into a lot of subtle functional things we've learned about the human genome, and we are increasingly understanding all the things that are encoded by those 3 billion letters. We've also learned a lot about how our genomes differ. And this is a key part of being able to apply it to medicine then, because all of our genomes are a little bit different. We're 99.9% identical at the DNA sequence level, but that means 1 out of 1,000 places we're different, which means if you add it all up, each of us has about 3 to 5 million spelling differences compared to any other person, roughly. Well, most of those are inconsequential, but a small subset of those are consequential, some in a good way, some in a not so good way, some related to health risks, and others relate to other attributes. But increasingly, as we layer on information about where our DNA sequence is different and how that affects how our genome functions differently, we're putting a whole picture together. And increasingly, that is empowering us to be able to then turn our attention to specific diseases and figure out which of these many variants we actually harbor are relevant to human disease. Now, diseases are complicated, and they're all different types of diseases. Some are rare, which is what we're focusing on today. Some are more common. Rare diseases are a little more tractable at the DNA level because it's almost always a single gene that is broken because of a spelling difference. And that you can see illustrated here. And this will be the focus of what we're talking about. And in aggregate, rare diseases have an incredible burden on society and the world's population. There's also more common diseases, diseases we actually bump into more commonly in hospitals and clinics, but these turn out to be a little more, actually they're a lot more complicated. They involve not usually just a single gene, and it's not just in the DNA. There's a lot more influence of the environment and social context and lifestyle and so on and so forth. When we look at the last 18 years, we have seen spectacular progress with rare diseases. We've gone, actually, if you go back to when the Human Genome Project first started, the day the Genome Project started, there were only 61 rare diseases that we knew what gene was broken, what gene had a spelling difference that made it not function. 61. Fast forward to today, the number is nearly 5,000. And every week, there's another one where we figure out what the basis is for that rare disease. So we have seen the greatest progress in rare disease research because of genomics and the reduced cost of DNA sequencing. And that has given us an opportunity to harness that information for clinical applications, as you're going to hear. More common diseases, such as shown on the right, we're making progress. It just takes a lot more to tease out all the smaller contributions of what are typically many different DNA spelling differences. But great progress has been made, and you can expect a lot more to be made in the coming decade. In thinking about going forward, I can tell you the Institute's looked a lot at how it can continue to facilitate genomics being used, not only for understanding how the genome works, but really understanding disease and eventually operationalizing this for clinical medicine. And so much has changed as we have seen genomics be disseminated. It's probably one of the most gratifying things I have to do as director of the lead institute at NIH for genomics, is seeing genomics used by almost every other institute at NIH. We've gone from once upon a time just getting the earliest magnified look at the human genome sequence during the Human Genome Project. But now the threads of genomics are being woven into this increasingly complicated fabric of biomedical research and of human genetics research and of computational research, and increasingly into the clinic as we're starting to see genomic medicine being realized. And it's not just one discipline using it, it's multiple different disciplines, and it's physicians and it's pharmacists and it's scientists and it's statisticians and it's computational biologists and it's ethicists. And this rich, rich fabric that's coming together with all these threads of genomics woven throughout it is really enhancing medicine. It's enhancing the research that goes on, and increasingly we think it's going to be beneficial to society. I'll give you an example that will set up the next speaker. And the example is, as we started to see the opportunities for using these new technologies for sequencing DNA and use them in other applications, one area of great interest was the idea of, should we be considering sequencing newborns, either healthy newborns, maybe not so healthy newborns, maybe newborns who are facing acute medical problems. So we partnered with another institute at NIH a number of years, actually shortly after I became director, and created a program that's actually now completed called the ENSIGHT program, the Newborn Sequencing in Genomic Medicine and Public Health. And it looked at both what is the benefit of sequencing acutely ill newborns and also the benefits of possibly sequencing sequencing the genomes of healthy newborns. And one of the things that came out of it, you're going to hear about, because the origins of the program that you're going to hear about next, or you'll hear from in 2 speakers from now, really do relate to some of the data that came out of this, and recognizing that time was now to actually use these new technologies of DNA sequencing for helping diagnose undiagnosed conditions in acutely ill newborn babies. So I will close by just saying we are very much looking towards the future. We spent the last 2.5 years engaged in the community to help us develop a new vision for genomics for the coming decade, the decade that we are now in. And late last year, in October of 2020, we published a new strategic vision for all of human genomics. And we published it in the journal Nature in these 10 pages. And I can tell you that all of the things being discussed today in this briefing are very much embraced by the things that we talk about in this strategic vision. And all of this is about really bringing genomics to the forefront of everything that we are doing, but particularly now, as we're going to discuss, bringing it to the forefront of the research and the clinical care of individuals affected by rare genetic diseases. So with that, I will stop and turn it back over.
Dr. Green, thank you so much. Thanks for your remarkable work to advance genomic medicine. And I'm pleased to introduce our next speaker, Ms. Sharon Terry, again, President and CEO of the Genetic Alliance. Please go ahead, Sharon.
Thanks very much, Susan and AdvaMed. Eric, thank you for all your work all these years. I've had the pleasure of working with Eric all these years as a lay person, and to Representative Peters for introducing your bill in the last Congress and for what we hope will proceed in the next. I'm Sharon Terry. I'm first and foremost a mom. I have 2 children, and in 1994, as Susan mentioned, they were diagnosed with a rare genetic disorder. That was after a diagnostic odyssey, a term that Representative Peters used, the idea that we who have children who are affected by something that we just don't know what it is are usually thrown into a tizzy, really challenged by this and don't know what to do. I think each of you probably can think of something in your life where you suddenly crossed a threshold, had your bubble burst, found something unexpected, whether in yourself or in a family member, and were just overwhelmed. And that's what happened Christmas 1994 for my family. After many years of trying to find out what was wrong with our kids, they were diagnosed 2 days before Christmas that year, and we were really, really glad to know. Lots of times people will say, well, it doesn't matter that we find these diagnoses, we really need treatments. And while I agree we need treatments, we don't have a treatment 26 years later for my kids. But knowing what they have and knowing what they're facing means a lot to us. And I'll talk a little bit more about that. I have a master's in religious studies, so I have no science background whatsoever. I know that that mirrors some of you. And I want to say that because of the work that Eric and others have done, it's much easier for us to understand what is going wrong when we're trying to face a diagnosis or find out how to get through the diagnostic odyssey. And in my case, I was lucky enough to be able to grab a bench at Harvard University and some postdocs to teach me how to clone a gene. This was before all the marvelous work that Eric showed, and so there was no easy way to do this. And it took us till 2000 to find the gene responsible for the disease my kids have. At that point, I was able to put together things like registries and biobanks and a support group and ways for people to gather around this condition to support each other. And that was very, very critical to the other parents and families facing what I was facing. So suffice it to say, it is not a nice place to be, and it's often a horrific place to be. You'll see when David speaks some of the babies that have been able to be diagnosed, and the differences this makes is really tremendous. And as we said, there's 6 to 10 million people affected in the US and more than 300 million around the world with rare diseases. This kind of medicine makes an enormous difference. And by medicine, I mean simply the diagnosis. After I did a few of these things, lots of other parents came to me and said, we need this for our kids. And again, this is the 1990s, late 90s. There's no internet. There's no way to communicate very easily with each other. But we set out to put together coalitions of groups doing this. And one of the groups was called Genetic Alliance, and I joined them as CEO in the year 2000. This allowed us to work with thousands of advocacy organizations, thousands of these patient groups, and to really start to do the kinds of things we needed together to support ourselves and our members, these millions of people living with rare and genetic conditions. I was fortunate enough to be able to lead a coalition that put together a force to pass the Genetic Information Non-Discrimination Act in 2008 after 12 and a half years of working on that. I know that that laid the groundwork for a lot of this, that we have that legislation in place. And so I know well how the sausage is made and how working together across the aisle, across the houses makes an enormous difference for changing policy in the US and allowing these technologies to really come to the fore. With these support groups working together, we are constantly looking at ways that policy can support the science and that policy can support the advancement of better care for our kids and for the adults who live with genetic and rare disorders. We do a lot of work matching individuals, so I get dozens of phone calls a week asking me to find some other kid in the world with the disease or the diagnosis that someone has just received. And so having this diagnosis as early as possible not only prevents a lot of the medical complications that one might see in these kids who may never walk or talk or thrive in another way, but also starts to be able to bring together enough of them to understand the condition. And there's quite a number of stories where individuals have found a solution because they got a diagnosis. So that's really critical. And then as Representative Peters said, it's really not just this medical piece, as you can well imagine. Again, thinking back to that traumatic event in your own family, it's the social issues, it's the financial issues, it's mom and dad are not able to go to work, they're going to multiple visits, they're going for multiple tests in various hospitals. And now the fact that a whole genome costs less than many times an MRI or a CT scan or some other kind of complicated workup is quite remarkable and a feat that I didn't think we would see this fast. And it's time to really use these tools. A lot of times I'm pulling strings to figure things out for these families, trying to figure out how they could get coverage and reimbursement and so on. And I'm really hoping that we can change that scene and give better access to all. COVID has only accelerated all of this and exacerbated it, as you can imagine. Certainly the financial situations of all, the ability to get healthcare, to get diagnosis have decreased. And at the same time, again, the simplicity of doing a whole genome sequencing on a person has really improved vastly. I want to tell you two stories that I think illustrate this, and you're going to hear a number of these throughout this panel, but I think it's important to put some faces on these. The first one is two women who I have had the pleasure and honor to meet and actually help them build a support group and build a registry only recently, this past year. Women named Debbie and Delaney, and I can name them because their story was in a TV show called Chasing the Cure. Essentially, they had very complex disease. The mom had suffered for 30 years with mouth and skin ulcers. Her joints had contractures. She had a peripheral neuropathy, so lots of difficulty and progressive blindness. She, though, despite all that, and by the way, also having a child with Down syndrome, was worried about one of her daughters, Delaney, because Delaney was progressing in the same way, exactly the same symptoms, coming behind her mom by a number of years, but having the same kind of difficulties. They went through more than 100 clinical workups and received more than 100 diagnoses that were wrong each time, sometimes with treatments that didn't work, sometimes things that probably made the illness worse. When they finally received whole genome sequencing, which was difficult for them to get, but they did through a philanthropic program at Illumina, this revealed that they were patients number 7 and 8 in the world with a condition called Warburg-Senati syndrome. It turned out that that gene is also mutated in a leukemia. And so there was actually a chemotherapy that might work for these patients. And so first the mom received it, the daughter received it, Delaney received it and started to get better. And then the mom did. This is only about a year ago. And as I work with Debbie and Delaney over these years, over Zoom, of course, watching the improvement in them, their ability to move easier, they're much less pain, and that Delaney went from being nearly legally blind to going back to painting and back to school has been really quite incredible. So again, just seeing, oh my goodness, had this mom been diagnosed all those years ago and Delaney been diagnosed when she was much younger, they would have gone through much less suffering. The other story is a child at UCSF, a little girl who's 3 years old. She presented at UCSF with multiple systems failure. So these are things like her kidneys were failing, her heart was failing. She also had some skeletal muscular abnormalities. So some difference in how she looked and how her bones and muscles were forming. The team there suspected that she had advanced mitochondrial disease, this disease of a part of the cell, and they determined to send her home to hospice because they said she's really just decreased in function so much, and all this multiple organ failure is too much for us to be able to reverse, particularly not knowing which of the many mitochondrial disease it might be. So again, another colleague there reached out to philanthropic program at Illumina. They did whole genome sequencing on this child and discovered that in fact she had a rare kidney disorder, a very rare one, and it had only been recently described in the literature. So recently discovered somewhere else, again, this kind of matching that can happen and give not only this clinical medical diagnosis, but also give a way for the family to say, we're not alone, we're with someone else and we're with others. And so in this case, they knew that they could do things as simple as aggressively managing her fluids, and she was stable within a week and went home a week after that. So you can imagine again that this simple act of diagnosing this child meant so much for these families and children. The last thing I'll say is that there is a sense that the haystack is made of needles. It's what's often said about rare diseases, that these are too hard for us to figure out. They're too difficult for us to discern. Where are we going to get, diagnosis and then bring these patients together? The technologies that have advanced, like whole genome sequencing, like the ability to do the kind of analysis that Eric showed, that any of us could just go right into one of these browsers and browse the genome, allow armies of people to be involved. I like to say I want smart Girl Scouts working on this stuff, just like any other part of our lives where crowdsourcing and where being in the long tail is not so bad. I used to use the example that if I wanted to find a rare book years ago, I'd go from store to store in different cities, and now I could use Amazon, and we know that actually Amazon even itself has progressed far beyond that. And so I don't think that this is like finding a needle in a haystack. I think the needle is made of haystacks, that every one of us can contribute to this kind of precision medicine, and that whole genome sequencing for the sickest of us is the first foray in this area. We've got to start with kids and adults who have been on this diagnostic odyssey for 5 to 7 years, which means and I know, some of them 20 years and 30 years, and this we don't need to do anymore. We really have the tools to address it, and we need to be doing that now. Thank you.
Sharon, thank you. You have really made very concrete for us the importance of these critical diagnostic tools. And thanks for your unwavering dedication, insight, and drive to improve the lives of individuals with rare diseases. Thank you. It's now my pleasure to introduce our next speaker, Dr. David Dimmock. He's the Senior Medical Director at Rady Children's Institute for Genomic Medicine in San Diego. Dr. Dimmock, go ahead, please, sir.
Thank you, and thank you for the chance to talk to you all about what I think is is one of the most important changes in healthcare that is happening right now. As Dr. Green alluded to, we were very privileged in San Diego to be a recipient of an NIH grant, newborn sequencing grant, really looking at the role that we had to consider with newborn screening in children. As a result of this project, we actually performed 2 randomized control trials comparing initially standard care testing with whole genome sequencing and then subsequently comparing exome with genome sequencing. We have been very focused specifically on critically ill children that are in intensive care units, and I want to focus on this because it is the area where I feel we have the most compelling data right now to start with this change in medicine. As many of you are aware, newborn screening has been the most successful public health intervention of the last 50 years, following much of the earlier stuff in the beginning of the last century, dealing with infectious diseases and immunizations. We will talk about slightly different numbers of rare diseases because, as Dr. Green alluded to, almost every week there's 3 or 4 new genetic causes of human health disorders described and published in the literature. And indeed, as a result of performing the INSIGHT 2 study on 213 children, we were able to identify 2 new disease genes, one of which is published and one of which is not yet published. As we talk about what we're going to do, I think Sharon alluded to a really important point, the value of knowing. And I'm going to touch a little bit on the value of knowing, not just from the parents' point of view, but also from the point of view of the healthcare providers as well. So having completed the INSIGHT 2 study where we sequenced 213 children, 40% of these results we returned in less than 3 days. We asked the parents and the physicians what they thought about this study and having genome sequencing. In the positive cases, 93% of physicians felt that the genomic test had utility. It was useful for them in caring for the child, even if there was no specific change in management that they could identify during the hospitalization. Similarly, 100% of parents from which we made a diagnosis saw this information as useful for taking care of their child, even in situations where there was no specific treatment. Much more surprising to us was that over 70% of the cases where we didn't make a diagnosis, the physicians felt that this was helpful because it allowed them some peace to move on from some of the rare conditions they were concerned that they might be missing. As a result of this successful randomized control trial, as I said, comparing exome with genome, we were invited by the legislature in Sacramento to consider a pilot project to evaluate this appropriate testing, where we demonstrated in a research setting that was benefit, to evaluate if actually in the real world, as we like to think of it, those benefits were maintained and what the economic impact would be on the state of California if this was provided to every child who had Medi-Cal. This project, which became known as Project Baby Bear, was a quality improvement project. That's to say we were acting on behalf of the insurer to evaluate the outcomes rather than this requiring research consent. This was important to the legislature because we know that there are underrepresented populations in research, and those are the exact populations that are much more likely to have coverage through the state Medicaid system. Participation was limited to Medi-Cal beneficiaries in one of 5 children's hospitals scattered throughout the state, both in rural and in more urban and suburban areas. These children had to be admitted to the ICU without a clear non-genetic cause, and the study, the data cuts we're going to talk about, ran from November 2018 to May 2020. We were fortunate that we had some philanthropy to continue this study for a little longer, and the publication that we are hopefully about to get out includes a slightly longer data cut. All patients received rapid whole genome sequencing with the goal of evaluating the clinical and the programmatic value of utilizing rapid whole genome sequencing as a first-line test in critical care setting. Go to the next slide. And as Assemblyman Peters alluded to, as a result of the initial 176 children that we sequenced, we made a diagnosis in 76 children. This was 43% of the kids that were sequenced. 35 of these conditions were so rare that they occur in less than 1 in a million births. And in fact, 2 of the children that we diagnosed, it was the first time these diagnoses had been made in the US in the preceding decade. 31% of the children that we sequenced, we had a direct change in the clinical management of the children. And I'm going to point out that the other 21 children, most of them didn't have a change in management because the physicians had a suspicion of a group of disorders, and so the child was already being appropriately managed. You can go to the next slide. The changes in management resulted in very dramatic changes in care. We had 513 fewer hospital days as a direct result of the intervention. The intervention is not just rapid whole genome sequencing, but it is, as Dr. Green alluded to, this concept of genomic medicine or rapid precision medicine. Having a diagnosis is not sufficient if the physicians don't understand that diagnosis, or they can't convey the information to the family in a way that the family can meaningfully use that to make decisions about their child's care. And so when we talk about the costs of what we do, I think it is important to understand, and this was included in the economic estimates for Project Baby Bear, that there is a cost of that medicine above and beyond generating genomic sequence and interpreting that sequence. Several children avoided very major surgeries, including a child where we were able to prevent them from having a very significant reconstruction of their throat and upper airway because of the disorder they had. We could put a breathing tube in a different way for a period of time. And essentially the defects in the upper airway we knew would be amenable to surgery, but at a much older age. And if we attempted too early, we would have disastrous consequences. Children often, when they are very floppy, if you don't find a cause from the frontline genetic testing, will typically have a muscle biopsy. Some other children would need liver biopsies. These are relatively unpleasant procedures to be done in a newborn. They require the kid to have general anesthesia that carries with it its own risk. Making genetic diagnosis in several children where a genetic diagnosis wasn't suspected had very dramatic changes in care. For example, a child was actually admitted to hospital with broken bones, and the concern had been that the parents had caused these broken bones. Making a genetic diagnosis of a disorder that actually leads to a child having very fragile bones that break very easy enabled that child to be returned back to their biological parents. Unfortunately, the disorder was fatal and the child did die, but as a result of a rapid diagnosis, that child was able to have palliative care at home with family and for those last weeks to be together as a family. We can go to the next slide. So I can talk about what it's like from the parents' point of view, but I am not one of the parents that went through this place. So I wanted to just show you a brief video of another one of the families who talk about the value of having an answer, even if there isn't necessarily a specific treatment that cures the disease, but does allow for more thoughtful management.
He was admitted into intensive care moments after birth, weighing only 2 pounds and 15 ounces. After spending 2 months in the NICU, he had begun suffering with unexplained seizures, digestive issues, and cataracts. His condition puzzled doctors, and every test failed to offer answers.
Our first hope appeared when our son transferred to Valley Children's Hospital in Madera. Doctors there told us about Project Baby Bear, a state-funded program to help critically sick babies in intensive care.
If not for a Baby Bear project, we would still be looking for the needle in the haystack. I would be blaming myself for his health. We're happy that we know what it is now.
I think the Project Baby Bear is a wonderful opportunity for families like ours to seek the answers and the help that they deserve.
So I can't underscore the importance it is, as Sharon alluded to, of having an answer. About 20 years ago when I was in training, I had the privilege of making a genetic diagnosis on a man in his early 60s who had suffered from a series of unclear problems for most of his life. His mother had gone to her grave believing that she had caused his problems because she hadn't been careful enough during pregnancy. Having this certainty of understanding what actually is wrong with a child has incredible value for families. Further, for providers, it makes a huge difference. If they know that what they're doing is the right treatment, they have much higher confidence in ordering and performing some things that are somewhat unpleasant to newborns, or similarly understanding and working with families when they believe that they want to do less severe or less invasive things. We've talked a lot about speed, and I think many of those on this call may know that our institute has really pushed the boundaries on how fast a genetic or a genomic test can be done. Why does this matter? Well, it matters for families to have answers sooner. It matters to providers because they can actually plan care knowing what they're dealing with, rather than feeling like they're fumbling around in the dark or doing what they always do, not sure if it's the right thing. Not only do we see those benefits, but actually it is cheaper to do a faster, more expensive test. And let me explain a little bit. If you have a child who is critically ill, they're in hospital for weeks, days, months, that intensive care stay is very expensive day to day. And in fact, rapid genome sequencing is considerably less expensive than 2 nights in an intensive care unit. By providing a test with a turnaround time of 3 days in Project Baby Bear, we saw over $750,000 in net cost savings from genome sequencing and the precision medicine intervention. If we had taken 7 days, and why 7 days is significant? 7 days is the fastest in our institution when we were all stops pulled out, but we can do a rapid exome. We lose over half of those cost savings, even though the test is slightly cheaper. And if we have 14-day turnaround time with testing, we're at a point where essentially all of the cost savings evaporate. So not only is it better for the children, it's better for the parents, it's better for the physicians, but it's actually better for the bottom line of the payer as well. One of the things that maybe stuck with you about the video is how Nathan's parents talked about the fact that they'd been in an outside hospital for 2 months before getting transferred to Valley Children's in Madera. This is one of the challenges we face right now, is that we have a limited number of sites that actually do rapid genome sequencing. And so it is not uncommon to have these stories of children that get transferred to a specialist children's hospital, when if the family had known the diagnosis 2 months earlier, we would have been able to intervene sooner, got the child home significantly sooner, and left the families and the parents without that 2 months of what is going wrong with my child. And this is why we really want to see rapid whole genome sequencing as something that is available to every child who is born in every hospital, regardless of whether or not there is a clinical geneticist on site. And if we can go to the next slide. We have taken this a little step further, and we have been able to model the 323 children that were sequenced at Rady Children's Hospital as part of one of 3 projects, the INSIGHT 2 study, the Project Baby Bear, and an earlier study where we did a more functional look at the economic impacts of genome sequencing on 42 children. When we take these 325 kids, it cost just over $3 million to do the sequencing for those children. Sequencing was more expensive 4 years ago than it is now. During their first hospitalization, we made around $4 million of cost savings as a result of that first hospitalization. So at this point, we have saved about $1 million compared with not doing genome sequencing. We were able to look at the costs of care for the first 5 years of life for a subset of 32 children that we had very high confidence in changes in management. And we were able to model a further $1.4 million of reduction in costs of care during the first 5 years of life as a result of these children not having the poor outcomes that they would have otherwise had. So when children have severe seizures and are neurologically devastated, we require less intense outpatient care. There are models of what it costs a family in terms of lost earnings and actual costs to deal with a child with significant neurological injury. And for these children here, again, we see about a further $1.2 million of cost savings. So in total, for a $3 million saving, expenditure, we save about $6 million of healthcare costs. And I want to emphasize that this is costs. Beyond that, we had dramatic improvements. We saved 2 of these children from significant brain injury. We saved 1 of these children's lives, resulting ultimately in a gain of almost 100 quality adjusted life years. Typical health systems are willing to pay between $50,000 and $100,000 per quality adjusted life year. And so this makes huge sense both economically and for the families, for the providers, and even from a healthcare system. If you were having to pay for this, the willingness to pay for this would be several $1 million more than the sequencing costs. We can go to the next slide. So right now we're at a point in the US where we are providing sequencing testing for a number of centers. In California, we've talked a lot about Project Baby Bear. There is a parallel project in Florida called Baby Manatee that has published prelim results, some demonstrating similar benefits. And in Michigan, they are launching a project called Project Baby Deer. If you're getting the theme, maybe you can hear it, where every neonatal intensive care unit in the state is going to be eligible to be doing sequencing, regardless of whether or not they have clinical genetics on site. And this will be provided to all children, regardless of their insurance. So not just the children on state Medicaid, but also on the commercial insurers as well. We have many stories from many states that are very similar to Baby Nathan, and we hope that we will get to fill in the gray states right now with this availability for such testing going forwards. One of the key hurdles for this fundamentally is the cost of testing. And this is why the federal match is so important, so that every child will get access to this across all 50 states. And I would just, if we go to the last slide, I would just like to say that our dream, our hope, is that every child who has a genetic disorder will receive a diagnosis, either at birth or at the time that they have their first symptom onset. But not only will they receive a diagnosis, but every family will have a supportive healthcare system with experts that can explain the disorder and implement either effective therapy or participation in experimental treatments or being provided with palliative care at that point of diagnosis. And with that, I would like to thank you for listening.
Dr. Dimick, thank you for your very powerful remarks and for your work with these children and families. Thank you. We do have just a limited amount of time, pardon me, before the end of session here. And I wonder if I might take the privilege of asking a question of Dr. Green, sir, please. And you talked a bit about planning for the future, but I wonder if you can tell us more. You know, since the launch of the Human Genome Project over 30 years ago, genomics really has become central in basic and translational research. And with major technological advances, we have next generation sequencing, et cetera. Where do you see genomics going in the next 10 years? It's an explain the universe kind of question, but I think you're very well suited to answer this for us and help our audience think about what is next.
Well, let me tell you, in answering that question, what we actually put in our new strategic vision published in October, because we even had a special section where we talked about bold predictions for human genomics by 2030, exactly the time frame that you're sort of thinking. And we had 10 of them, but let me just read 2, because I think they follow very nicely from the previous 2 speakers. We basically said one prediction was going to be the routine use of genomic information will have transitioned from boutique to mainstream in all clinical settings. making genomic testing as routine as complete blood counts. And while that sounds aspirational and maybe a bit inspirational, it's not out of the realm of possibility. That we'll just think of a genome sequence as a CBC. I'll leave you with one other of our 10 bold predictions. Breakthrough discoveries will lead to curative therapies involving genomic modifications for dozens of genetic diseases. Because at the end of the day, of course, that's what we'll be looking for as well. Now, these are obviously really big reaches for both of them, but I think what you've heard today in the arc of discussion is I don't think they're out of the realm of possibility for the coming decade.
Thank you, Dr. Green. And what we'll do for all audience members, within 24 hours of the conclusion of this session, we'll send an email to all of you. We'll provide a link to the recording, to our speaker's slides, and to additional materials, such as the publication Dr. Green just mentioned. If you have any questions, please do respond to that message, and we would be delighted to ensure that we can get a response to you. I want to thank again all of our remarkable speakers for your work, your dedication, for taking the time today. I want to thank Congressman Peters for his leadership, and to all the members of the audience, thank you all for spending this hour and a half with us. We look forward to working with all of you to enhance and extend the reach of genetic testing for all individuals with rare diseases and beyond. So thank you all very much.
Bye-bye.